All right. Hi, everyone. Welcome to today's stream, which is an excuse to practice my PCB design skills for a workshop I'm having Friday. Actually, I think this would be a better place for my webcam for this. Hello, hello. You'll notice that there's no chat today, because I'm eventually going to use this recording as a guide for PCB design. We're doing the whole thing from start to finish in one recording. This will probably take 2 to 3 hours, but I feel like it's good practice for me, and later on we can use this as a base model for how to do PCB design. So this will be a little bit of a comprehensive guide. There's no music in the background because I don't want to get this copy striked. There's no chat. I'd probably turn off the alerts too, just for today. I think the sound still might be in the background, but they don't show. Okay, and I apologize to chat because I know I haven't. This is the first time I'm streaming in like 14 days, I think. It's been 2 weeks, but I will answer some questions from chat, but I won't be paying too much attention because this stream is meant to be a guide for PCB design in the long run. So hopefully we can get this through. This is not pre-recorded, Kandar said. No, it's not pre-recorded. I don't remember how to stream too well. But at least I got the mic right, I got the transitions right, and I got the webcam right. The webcam's fixed, by the way. This is the NVIDIA broadcast webcam. It's not like the one where I did a display capture and and looked at it. How did I predict you would say that in the recording? funny. So I'm hearing race cars in person this season. It is, which will be a lot of fun. Okay, so today is going to be the practice run, and let me just make sure my audio is working. Actually, I don't even need audio today, so I don't know why I'm having that. And you'll be able to see basically everything, the whole process from start to finish, hopefully. Might be an intermission in the middle, but we're going to go over some things and, go through the whole PCB. So this is pretty much going to be my practice run. Let me just get this for a second. This is my practice run for the workshop on Friday for PCB design. For those of you who just came in. Okay. You can open KiCad and play along. I mean, it isn't a play along thing, but you can follow along if you want. If that makes sense. Okay, so assuming that you have... I'm going to be speaking to the viewers now, and not too much of the chat, just pre-warning. I assume you have downloaded KiCad, and it's been so long that since last stream that KiCad 7.0 is now out, so I have to upgrade systems. And we're using KiCad 7.0. The first thing I'm going to do is download some plugins. The plugins we're going to be using are Interactive HTML BOM, which is the plugin that allows you to generate a bill of materials as a interactive HTML. It's a very useful plugin. And also, I downloaded some color themes, including the Solarized Dark and Light themes, and the W Dark theme, which I'm actually going to be using today. So these are really fun schematic colors that, allow you to work in dark mode. Bad Nightbot. Bellum, can you fix that for me? Thanks. Okay. So, and I know that Bellum has also been leaving comments on every single video so far. I think he's starved for content. Okay. So in order to change your theme in KiCad and make it a little bit more nice to look at, you will go to Preferences inside of your schematic. So if I double click on this, it'll open a schematic here. If you go to Preferences, I believe, on this schematic here, and go to Colors, you'll be able to change your theme from the KiCad Classic to Dark theme. This is easier on the eyes and just looks good and better overall. Okay, give me a second here. I'm just going to disable the Discord so I don't accidentally click on it, because I know I will eventually. Okay. This is going to be for a workshop I'm running on Friday on PCB design. I usually stream it a few days before for a trial run. year or last semester, I actually had a stream in which I learned KiCad, and we did the voltage regulator circuit. But this time I'm doing it for in one stream. Last semester it was a couple streams, but this time it's just one stream. Okay. I don't know if the bong will go off. I kind of disabled the alarm system, but you're welcome to try if you want. That'll be a fun little Easter egg for those watching in the future. Will I ever stream during a workshop? There are too many liability issues for me to ever stream during a workshop, unfortunately, so I will not be doing that anytime soon. Okay, let me just make sure my webcam settings are optimized. It's gonna bug me if it's not. Okay. But hopefully you guys are having a great day today. It is the middle of the week. It's Wednesday. Tomorrow's Thursday. Oh, hold on. Spending way too much time calibrating my webcam here. Okay. So, the idea for this workshop is to build a 7-segment display decoder, which allows users to input a 4-bit number and have it showcase itself on the display. It's meant to be a simple circuit because it's a circuit that a lot of people use, especially in 2300 or in this case, digital logic class in electrical engineering. So it's meant to guide students along this kind of routes, and that's what we're going to be doing today, building a 7-segment decoder. Now, I do have the a previous schematic I'll be referencing on the side, but in general, I'm going to treat this as if I'm teaching the workshop and just go from start to finish. The workshops will span for about 2 hours, but I have to design this for 1 hour. So it'll be a little bit rushed during the workshop, but in today's stream, I can make sure that each part is nicely made and just neatly made and whatnot, and don't have to worry about time constraints and all, because I can be here for as long as I want. I can make this like 3-hour stream if I wanted to. So in general, there are a couple components to this PCB, and to add a component to this system, we're gonna go to the place bar and click on add symbol. And inside this filter, the most important part is going to be our decoder. So we're using the 74LS47 chip, which is the BCD to 7-segment driver open collector 30-volt outputs. You can click on that. Okay. And this is going to be our decoder. So you'll see here that this chip works as, such. You have 4 inputs representing the 4-bit number, A being the least significant bit, and D being the most significant bit. You have control pins, which will all be linked to 5 volts, just because we don't want things to be cleared or reset. These are all inverted, so if you can the 5 volts, they'll turn on. You have VCC and ground, which is standard on every DIP chip, just for external power. And you have 7 output pins on the right-hand side. And these will connect to the 7-segment display, which has 7 segments, representing the 7 LEDs, and they will turn them on and showcase a number. So obviously, we're going to go ahead and try to find out the 7-segment display. Now, I'm not sure if this is actually a symbol that's inside of KiCad, which I'm taking a look and I'm seeing that it's not. So this will be a symbol that I'll have to copy paste from another file, or I'll just provide this to the students on the day of the workshop. So we have the decoder and the 7-segment display, which are the core components of our circuit design. And to the inputs of the 7-segment display, it's just 7 LEDs represented in this kind of 8-figure that showcases a number. So we're going to just connect it directly from the output of the decoder and into the input of the 7-segment display. In general, for an LED connected to a basic LED circuit, you would need a resistor in order to prevent a short circuit, because a short circuit's not that great. So every LED internally in this module is connected to a common 5 volts or common ground usually. In this case, because it's a common anode, every pin must be connected to a 5 volt signal, in which you can get a 5 volt signal by going to place and add power. If you go to power, you have a bunch of power options, but I usually use the 5 volts and I use the ground. So we'll have a 5 volt signal here and a ground signal. Let's just get a G and D. There we go. Okay. So in this case, I'll put the 5 volts right here and the ground right here. This creates a net. So whenever I use this 5 volt pin in the future, it'll all reference the same net, or everything will be connected to this 5 volts. So the common anode is going to be the singular pin that connects to all of the input pin, which means in order to turn an LED on, the input must be a 0, right? It must be a low signal. So if the input is a low signal, then the circuit will complete, right? And the current can flow through the right side, through the LED, and into the ground on the left, or the low signal on the left. We'll also connect all the pins, all the control pins, to 5 volts, just again to make sure that it doesn't, make sure all the control pins do not reset the 7-segment display erroneously. And we'll just make a label as well. To make a label on your circuit, just press the T button. That opens up the text properties, and we're going to type in 7-segment display circuit. Okay. And I'm not sure which font size this is, so I'll check here. Text size 0.075, so I'll just repeat that here. And okay, place that here, and we're done with our text. Okay. Now we've gotten one part of our circuit. This circuit, what it does is it accepts a 4-bit input and decodes it into a decimal number that can be displayed on a 7-segment display. Now, the 7-segment display is, and I see in the chat, I have, why are there 2 C8 pins? 7-segment display has 10 pins, right? And there are 2 common anode pins, one at the top and one at the bottom. And there's also a external pin for decimal point, although you don't really use that, so that can be just connected to air. In this case, these 2 pins, when you're working with a breadboard, they're for easier access, and you can access the common pin, or the common 5 volts, from the top or the bottom. But pretty much what this does is we have to put in 4 inputs to the left side here, and this will give us our inputs and our outputs of the circuit. Each common anode pin runs a separate section of LED, so you're not overcurrenting a single pin or something. That is also correct. But some common anode displays I've worked with don't actually have that, because they are cheap Chinese models, cheap Chinese LEDs from China. Okay, now the inputs, we can temporarily right now create a net label for them, or a net, and we can call them the inputs of our 4-bit input. So to make a net label, all you got to do is go to place and add a label L here. I think this is the right one. In this case, I'll name these labels O. And these will stand for like different outputs. So I'll have O1 here, O2, O3, O4. So pretty much how these work, these net labels works, they're like portals. So you can think of them as if I use one of these net labels, like O1, O2, O3, or O4, somewhere else in the circuit, they are physically connected together on the PCB. Also, thank you for the sub, Bella. So now that we've completed one part of the circuit, we have to think of what else we want to put as a user utility mechanism for this PCB, in which if we have the way to convert a decimal or a 4-bit number into a decimal number, in this case it's not actually decimal, but configuration of outputs that shows a decimal number, we need some way for the user to put in an input. In this case, we'll have a series of switches, SPDC switches, that allows the user to do so. So we're going to go ahead and make a user control circuit using switches. So imagine when you have the completed PCBs, there's a bunch of switches in an array that you can flip on and off to provide the circuit with a 4-bit number. And the switches will either send a high or a low signal into each of the pins. So what I'm going to do next is go to add symbol and find myself an SPDT switch. SPDT stands for single pole double throw. So single pole, meaning there's one pin on the left, two pins on the right. And for a 4-bit number, I will copy paste this 4 times. Just so we have 4 of these right here. So what we're ending up in this situation is each of these switches will connect, you know, maybe like a 5-volt signal to the rest of the circuit, right? So in this case, we can put a 5-volt signal right here, pretty much giving one side a constant 5 volts and the other side a varying ground, which means that if we connect a switch, the 5-volt signal will complete the circuit and it will send a 5-volt signal or a high signal into the decoder here. So I'm also going to go ahead and just preliminary put no connects on the bottom SPDC switches. We're not going to use these. We're just going to keep them connected to nothing. Now I'm going to take this a little bit slowly in order for me to connect this to the outputs. So I can pretty much go ahead and just connect this first one to O1. And remember, when I use net labels, this end and the beginning of the decoder are connected together. I can connect them together like this, and that would work the same way. But if I do that, it'd be a lot more confusing. And eventually, when I put like all the components on this PCB, it would be really confusing to understand because you have wires going everywhere. So I like to use net labels as a way to simplify things. So in this case, I will put the O1 symbol on the right-hand side here. And you can just imagine there being an invisible wire going from this pin all the way to the beginning of this decoder. All right, so now if the user would switch this switch from the 1-2 position to the 2-3 position, right? It will basically cut off the 5-volt signal to O1. Right now, when the 1 and 2 pins are connected, right, it sends a high signal into the decoder, which, you know, it's O1. However, when it's disconnected, it will leave a floating value, or it'll leave some... the decoder won't know if the logic is high or low. So we need to add what's called a pull-down resistor in order to showcase to the O1 or to the decoder that when the switch is not, you know, flipped in the correct direction, or when the switch is flipped off, it has a 0 value to look at, right? So I'll currently put a 1 value here just to indicate that if the switch is in the 1-2 position, then a high signal will go from the 5 volts into the decoder. But otherwise, we need to add a resistor, and I'll just put R here. We need to add a resistor to connect or to pull down the signal to ground if the switch is disconnected. If we flick the switch off, right, we need this signal to be pulled to ground, giving it a 0 signal. So if I can just go ahead and not screw up here and copy a ground signal, put this on the bottom of the resistor, and connect this junction. I will rename this resistor to 1K. We'll call this a 1 kilo ohm resistor. And you'll see that in this case, we have the SPDT switch connected to 5 volts. We have a 1 signal, but if it's connected between 2 and 3, then this pull-down resistor pulls the signal down to ground, providing a 0 voltage, or 0 volts, which the decoder can read as a low, or a false, or a no. So this is kind of the same logic we're going to use on all 4 of the switches. The cool thing about this kind of circuit design is once you get it working the first time, then you can just copy paste it for the other 4 times. And in this scenario, we can just do a bunch of these resistors. I'm going to delete this signal because once we have like one working model, we can just copy paste it. So I'm just going to copy paste it here like this. And then I'm going to go ahead and just connect these switches to the resistors right here. Like that. All right. Now it doesn't have to be any like coherent order, but after this, I'm going to press the W key to create a wire. And I'm going to extend these SPDT switches or the signals out to the right, which I'm going to use the net label in order to connect this circuit or this array looking at the structure here to the outputs. So in this case, this first switch will go to O1. So again, imagine the invisible wire going from the right all the way to the left. This O1 is connected to this O1, and it's the same logic with O2, O3, and O4. I like to think of them as portals. And I like this way of organizing the circuit, although I've been told that it makes it really, really hard to read. Okay. So, now that we have this kind of logic, I'm going to go ahead and, again, label this as the user input circuit. Because the user is now able to choose whether a 1 or a 0 to put into the circuit, right? And that gives the circuit now an input and an output. So if I can go ahead and label this as the inputs here. This will be like the purpose of each circuit here as we go through the diagram. And we can have an output. Okay. All right. So let me just position this a little bit better so we can have this along the side here. Great. So what else do we need in the circuit? The first thing I'm thinking of is something that can be helpful is maybe an array of LEDs to indicate that things have been connected to the circuit. And LEDs, again, a simple LED circuit is just going from a high signal to a low signal with a resistor between. So this will be a simple resistor connected to a diode or an LED, which we can grab straight from the place menu again, so symbol. So in this scenario, we have the resistor connected to an LED, connected to ground, and our potential 5-volt solution is going to be our output node right here, right? So we can construct this circuit by saying, theoretically, O1 can be 5 volts or 0 volts, depending on what the user chooses, right? From the user input circuit on the left. Therefore, we can connect O1 straight to the resistor, straight to the LED, and then straight to ground. And if O1 is 5 volts, which means if the switch is flicked on, then the current will pass through this resistor, it'll pass through the LED, and it'll go straight to ground. All right. So because of this, we'll go ahead and copy this again, because this is just the same exact circuit for 4 times. And we'll just minimize it a little bit so it's easier to look at. There we go. And we'll just copy this 4 times and place it all next to each other. Okay, great. So in this case, I'm going to go ahead and change the O1, O2, O3, O4, like this. Now, the point of this circuit, or the circuit will work based on what O1, O2, O3, O4s are, right? And this net label is dependent on what the user chooses. If the user wants to turn O1 on, they can just flick a switch. Otherwise, they won't flick a switch. All right? It's a pretty simple circuit, but it's a very valuable one because it provides user information as to what they have done with the circuit. It's kind of like user validation in a sense. You want the user to understand what they have done inside of the circuit so that they can understand and troubleshoot if something goes wrong. It's when you flick the switch, an LED will light up. We do know this is going to work. So if this doesn't work or the LED doesn't light up, then when we're troubleshooting this PCB, when we order it, we know something's wrong. Right? It's kind of like fundamental knowledge, but in the sense of PCB design. So I'm going to go ahead and label this circuit as 4-bit binary LED circuit. 4-bit binary LED circuit. And we just need to remember that O1 is LED, O1 is the LSB. This circuit is to provide user validation. It's a debug log for circuits. Yes, that is basically it. We just need to make sure the circuit's working. So, now that we have these 3 circuits, the circuit's actually almost done. We just need a last module. And the last module is to deal with any power that goes into the circuit. Because when we're designing, we need to make sure that the circuit has sufficient power. And not too much power and not too little power. It's kind of like the Goldilocks of circuit design. You want to have just the right amount of power. So, in our circuit case, if this circuit receives too low power, it's not going to damage anything. It's just going to turn off and not work. So it's not our fault that the user doesn't put enough power in, but, we just need to make sure they put enough power in. Now, it's dangerous if the user puts too much power in because, if you stick this into the wall or inside the live city power, this circuit's going to blow up. So we need to make sure that the user doesn't put too much power by regulating it down to a certain value. And The way we're going to do that is to make a regulator circuit. Now, the most basic regulator circuit I can think of is just to use a linear voltage regulator or fixed voltage regulator, something like the AMS1117. I like this chip because it's small, it's compact, and it comes in fixed voltage regulator modes, or FVRs. So if we search up AMS1117, you'll see that KiCad actually has a bunch of fixed voltage regulator models for us to choose. So in this case, I'm going to select the 5 volts, because this decoder chip runs on 5-volt logic. If you take a look at the data sheet, you'll see that the input range is somewhere between like 4 volts and 6 volts, usually. And it can tolerate stuff up to like 12 volts almost, but for safety, we're going to assume that the user's going to put like 9 volts into the circuit to power it up. And we're going to need a way to regulate it down. The AMS1117 is a pretty simplistic chip. Really not that difficult of a chip to understand. You put in a voltage that is going to be somewhere between like 5 and 12 volts. I think it can even go very higher. I'm just giving a ballpark number here. Let's say 5 to 12 volts. And then on the output area, you're going to regulate it down to 5 volts. And, you know, you connect the ground to ground. It's a very simple circuit. And, you know, there's not much really to argue here regarding the functionality of this. It's not the best of like voltage regulators. Buck converter would be definitely better for the situation, but you also have to take into account the cost. Buck converters are notoriously more expensive than AMS1117s. Like one of these chips is about 4 cents. Buck converter, about $1. So it all depends on your application. But we're going to go ahead and just connect this to a input circuit, or input power circuit, excuse me. And we're going to regulate that down to 5 volts. So I'm going to put a wire here on one side, a wire here on the other side, and I'm going to place some power indicators, maybe one for 9 volts here. Let's say I'm connecting a 9-volt battery to it, and the other one being 5 volts. Oop. Right here. Great. So now I have a way of putting in 9 volts to the circuit and getting 5 volts out from the other end, and I have a ground too. But, you know, with all these linear voltage regulators, for the most part, if you need to make sure that whatever voltage or whatever signal you put into this chip is clear from any noise, or like any signal noise, as we call it. Because this chip has a bunch of transistors inside of it that work meticulously to get the voltage down to a certain level, which means you need to make sure that the signal going into the chip is free from noise as in something that messes up the signal voltage. Kind of like in an earthquake, a seismograph will display like really shaky signals, like this, what I'm doing with my hand right here. You want to make sure that the voltage is very clean and travels in a straight line with respect to time. So in order for us to do that, we include capacitors to filter out this noise. And we must include them both before the chip and after the chip, because they act as kind of like filters, like large-scale filters and small-scale filters. So what I like to do in terms of filtering out the noise for these AMSs is I will include a capacitor here, and I usually put 2 capacitors before and 2 capacitors after. And capacitors, I usually have to put 10 microfarad capacitor and a 0.1 microfarad capacitor just to filter out any sort of noise I get. And I'll do the same thing on the other side. Now, this may be overkill, by the way. You don't need this many capacitors in your circuits. I just do it because, you know, it's clear. It's a clear signal overall, and plus, it looks visually better on the board to have these on. But if you just want like one capacitor on each side, you're more than welcome to include that. You don't have to put like 4 like I'm doing. You just need a capacitor, because without one, your signal is going to look really messy, and the regulator might not regulate it to the right value. It might not be a 5-volt signal. It might just be like a 4.7 or 5.2 or something inaccurate. The datasheet for the AMS recommends these 2. Yes, that's correct. So now that we have our regulated and filtered circuit, and we have a smooth 5-volt signal coming out from the other end, the next thing we have to do is to ensure that the user has some way of putting the voltage into the circuit. Because right now, all we have is the 9 volts signal at the very beginning. That shows us nothing, right? That doesn't tell us how the user can put this 9 volts into the circuit. So I'm going to go ahead and just put this up here, like by 1 block, just so I can, raise up. We're going to remove this 9 volt signal right here and allow the user for a way to put the signal into the circuit. And one way to do that is to use a terminal block. So I'm going to go ahead and go to add symbol. And I'm going to type in terminal, and this will come up with a bunch of screw terminals. You have a lot of screw terminals. I'm going to use the 1x02. And this 1x02 screw terminal will allow me to, actually I'm going to position them so one is on top, like this. I'm going to rename this to VN. These screw terminals look like the little blue pieces in electronics. I don't have one on me right now, but it allows you to insert jumper wires or jumper cables into them. I really like these. I have like tons of them. I have 1,000 of them in my bag. But it allows you to screw the wires shut so that you can't remove them, and it keeps your power input safe. Because for a lot of applications that I work with, I'm really scared of shorting the 2 input terminals. And the better I can keep them safe, or like the better I can secure them, the safer I feel overall. So, great. We have a way for the user to put in a 9 volt battery into the system and power it up, because we're dealing with power here. However, and this is what I'm going to say for this kind of situation, the user may connect the battery backwards, and it may cause some issues to the circuit. So in order to protect against that, to protect our circuit from the potential of the user trying to destroy it by flipping the input pins, because, what happens is that if you flip the input pins, that's called reverse polarity, current flows in the opposite direction, and if current flows in the opposite direction into this AMS 117 regulator, there's a bunch of transistors inside of this, and if you do reverse polarity with transistors, sometimes they'll create unnecessary shorts, which can make it heat up and catch fire and just plumes of wild smoke in the air, which has happened to me before. So to protect against that, I'm just going to use a simple diode. Now, in this case, remember that diodes have a voltage drop across them, which means if I use like a 4001 or 4007, it's about a 0.7 to 1 volt voltage drop. So if you're using a 4 volt input source, this is not that optimal, or sorry, 5 volt input source, because it'll drop it down to 4 volts, and then maybe your decoder might not work properly. So if you want to use a diode, I'm going to use a 4001 diode here. Diode. So if you don't want a voltage drop across your circuit, you can use maybe a NMOS or PMOS. PMOS is probably pretty preferred. Or some gate that prevents reverse polarity, but also doesn't have that voltage drop across it. That makes sense. Like once the PMOS is in saturation mode, the current can flow through. If it's in cutoff mode, then it won't have a voltage drop across it, right? So I'm going to put this directly across from the input of the voltage, 9 volt voltage, and put this into the circuit like this, right? So the user is able to put, and I'm going to put a ground right here. The user is able to put in a 9 volt battery into the system, and it will go across this diode, making sure that the current is flowing in the right direction. Again, diodes are like one-way bridges or one-way paths. Current can flow through it in one direction, that's called forward bias mode. But if current flows it, or current tries to flow through it in the other direction, which is reverse bias mode, it won't let it, right? It's kind of like a wall. It's not going to let the current go through. So this is protected. We have protected our circuit. Everything is nice. Everything is cool. Everything is good. Now, in order for us to make this circuit more, utilitarian, I don't know if that's a good word to use, we need to include a switch, because if you're like me, I leave my circuits around a lot, and if I'm not using the circuit, I want to turn it off, right? In this case, in this scenario with my circuit here, if I wanted to turn the circuit off, I would have to remove the battery. In this case, removing the battery would be removing it from the terminal block. And I don't want to do that because I have way too many things already, and it just gets messy overall. Easiest way to fix that, add a power switch, right? Power switches exist in pretty much all electronics, right? Your computers, toys, I don't know, other PCBs you might be working with. Power switches are good because it allows you to keep the power source within what you're building without having to remove it from the circuit. So I'm going to go ahead and copy one of these SPDT switches to my power circuit here. I'm going to cut this part off, and I'm going to put the switch in between, like this. Now, what happens is I'm going to connect the switch to my 9-volt battery, and then the top of it to the diode, which completes the circuit, right? If the switch is flipped in the other direction, that's the quote-unquote off state. So we can just put that to a no connect symbol. I press Q there to get a no connect symbol onto my schematic. So in this scenario, we have finished adding some user input, quality of life improvements to our circuit. Now the user can, relax and use their circuit normally. They have a bunch of switches they can use to turn it on. And they have diodes so they don't connect the circuit backwards. It's really nice. Now, what happens with the power switch, you gotta just make sure you check it on a circuit once in a while. Even though there's a switch, connected to your circuit, a switch is just made out of thin pieces of metal that connect together and create a short circuit on one end and not on the other. However, there's something called parasitic power because it's still made of metal, right? So a small amount of leakage current can travel across the switch and into the rest of the circuit, even if the switch is turned off, right? And that's a problem because over time, your battery will run out because of this leakage current. However, this is over time, and it doesn't really have an effect on the short run. If you're storing this kind of model inside of a storage unit, for 10 years on end, and you come back to it, of course the battery's going to be dead because, you plugged it in, parasitic power exists. But you don't have to worry about it as of right now. It's just a small concern that you might face in the future. I just got a chat message that says, add a buzzer if they plug it in backwards to scare them. That's funny. So, I'm going to add one more quality of life improvement to this power circuit right now. And that comes from the, indication, again, user validation. You want to make sure the user knows what's going on in the circuit at all times. Easiest way to do this, you can use a buzzer, but easiest way to do this is use an LED, right? If the user turns on the circuit, you want to let the user know that the circuit is on, right? So we can add an LED circuit, just a small one, and then we're just going to grab these components from the top here. You can add a really small LED circuit here to the diagram, in which it goes from after the diode into this LED, into this resistor, into ground. This is just to allow the user, or to tell the user that, hey, your stuff is on, right? Because it's good for them to know. Otherwise, they might not know the circuit's on. Also, it's really good for troubleshooting, again, because you're making this PCB from scratch. You're eventually going to order it as a Gerber file from JLC PCB, and when you're soldering it together, you need to make sure that each step of the PCB works. Easiest way to do that is to use an LED, because it tells you that, hey, the circuit's getting power, because it's connected to the input power source. If the circuit does not work and you connect it backwards, this is not going to light up and you're going to go, oh, I accidentally connected it backwards because the LED is not turning on. Again, great user indication model just to let the user know that, your circuit works. Same for the other LEDs. So great. We've now went ahead and created a power circuit. I'm going to go ahead and name this as power input circuit. So all kind of electronics need some sort of power input like this, obviously, because you might not have the correct battery to power this. It might be over, might be under, but if it's over, you're fine because you can put it in. I usually use 9-volt batteries. I have a ton of them. It's not because I accidentally put in an order for Amazon and had it automatically deliver $3 to my house every month and I forgot about it for 2 months. But 9-volt batteries are generally pretty good power sources. I built my own little power sources for this project here. And they work pretty well on 9-volt batteries. You know, the only problem with 9-volt batteries is they don't have a lot of current. You can't draw too much current from them. And the current limit is about 0.61 amps. So if you're powering a drone with it, probably not the best idea. But 9-volt batteries are pretty good. So are 18650s, but you know, they have a lower voltage per cell. If you use multiple of them, then you have to like do balance discharging, balance charging. It gets more complicated over there. So in this case, we're going to put this power input circuit on the right-hand side. And this is going to be our last component of our diagram. We have 4 modules. We have the 7-segment display circuit, which is the brains of the circuit pretty much. It's what holds all the logic inside of the circuit. We have the input as the 4 bits, which are designated by the user. And we also have a 7-segment display on the right, which is the output of our circuit. So in this scenario, moving on to the user input circuit, I realize while I'm doing this rehearsal, I'm saying like a few of the same phrases over and over again. It's kind of annoying me, but hey, that's why it's a rehearsal, right? So the user input circuit is going to allow the user to choose bits. You know, choose whether they want a high bit or a low bit. In this case, we have 5 volts attaching to the switch. If the switch is in the 1 to 2 position, it allows the 5 volts to flow into the O1, which, and again, this is net label, so O1 goes directly into the input of the 74LS47. If the switch is flipped off, so it's in the 2 to 3 position, you can see the current won't flow through from the 5 volts, but this will pull it down to 0, which allows O1 to have a 0 signal, or it shows to the chip that you're giving it a low signal. Otherwise, if you don't have this, it'll be very confused because it's just floating, right? It might think it's a 0 or a 1 because internally inside the 74LS47, it has internal, like, small amounts of current that goes here and there, traveling around the internal chip highways. So in order to make sure and prove to the chip that you're giving it a 0 signal, put a pull-down resistor. Pull-down resistors usually can be anywhere from like 1,000 ohms to 10,000 ohms. Doesn't have to be too like egregious of a value. It's just to make sure that, you know, you have a ground signal, right? You're showing that ground exists. So, next module is the 4-bit binary LED circuit, where we talked about user validation, or user... Did I say user validation? It's like proving to the user that your circuit works, right? And these LEDs are directly connected to the user input switch. So the user input switch will flick on or off. It'll connect directly to the 4-bit binary LED circuit, and these LEDs will light up if the user turns on the switch. It's a direct effect, which proves to the user that, you know, that part at least works. And last but not least, we have the power input circuit. I realize I dragged this away. But the power input circuit, its job is to regulate the input power source to your PCB by turning 9 volts to 5 volts, and to allow you to have switches. So the power input circuit regulates the input of power from 9 volts to 5 volts through the fixed voltage regulator. I'm doing this again because I know I said it out of order. So the regulator has a lot of utility that we've talked about during the last semester's workshop, in which allows it to give a clean 5-volt signal into the circuit such that it works in its best way. One of these ways to make sure the output is nice and clean is by using these capacitors right here to filter out any noise that comes in or out of the fixed voltage regulator. In addition to this, we also added 3 types of quality of life changes to the circuit so that the user can experience it better. One of these is reverse polarity protection using this diode. It prevents the user from connecting the battery backwards and damaging the circuit, because the diode prevents current from flowing back the other direction. The next thing we have is a switch. The switch allows the user to turn off and on the circuit if they want. You know, turn the circuit off if they're not using it, turn the circuit back on if they want to use it again. After my mistake of not putting switches on some of my PCBs, I've then learned that switches are very, very useful for a lot of applications. Then we have an LED. Now this LED here is for indicating to the user that your circuit is on. It's a pretty cool piece of equipment. Okay, so now that we've gotten the circuit made, and that's going to bother me for a lifetime, this positioning thing. Now that we have our circuit constructed with all the 4 modules, what we need to do next is assign footprints to all 4 of these circuits. Footprints are what's going to be on the PCB schematic when we eventually make it. It's kind of like it's the blueprints of what makes each component. I'm going to move this here. And then move this over here. So in KiCad, the way you assign footprints, or the way you make sure that each of these symbols has its corresponding footprint, is you use the footprint assignment tool in the top here. This footprint assignment tool, or this library, will load a bunch of stuff, and it would provide you a lot of options into making sure that each symbol has the right footprint. Because currently in the circuit schematic, they're known as symbols. Oh, in KiCad 7.0, they show it as yellow if it's not chosen yet. That's pretty cool. So I know that for the 4001 diode, it needs the 7.62 millimeters model because the 10 one is a little bit too large. And for the rest, we're just going to follow some pretty standard things. Now, I know that I accidentally uninstalled everything, so I currently do not have my custom components. My poor custom components library is just gone. But we can go ahead and make a new one, and we can make a new custom component based on the datasheet of the 5mm switch. Okay, so we'll do that last. And I'm going to base this footprint assignment tool on what I had previously for the Blinky Learner 2, which is like right here. Don't worry about that. Yeah, see, it says the 5mm slide switch is gone, so we're going to practice making the footprint again right here on stream. And I don't exactly remember how I made it in the first place, so it's good practice. Okay. Okay, so the 10, let's do the resistors first. The resistor footprint is going to be, the way you find footprints in this list is, I'm going to turn on the filter footprints here. On the left here, you have the footprint library. So it's grouped up into libraries, which all contain individual footprints underneath it. KiCad by default has a bunch of libraries KiCad has a bunch of pre-installed libraries, which is like one of the best things about the program, really. And we can find out the resistors by going to the R section and choosing the resistor underscore THT. Now, this stands for through-hole component. So this resistor underscore THT is going to pop up a bunch of stuff on the right here, in which we can then filter it out by typing in the dimensions of what resistor we want. So we want L 3.6 millimeters underscore D 1.6 millimeters, and then underscore 7.62. You can actually see what this looks like by going to this symbol right here. It says view the selected footprint in the footprint viewer. And it kind of looks like this. And this is the exact dimensions. If we look at the footprint here, it goes 2.54, 5, 7.62. So we'll know that the resistor is in the correct value. Now, if you're making the footprint on your own, you'll have to do like measuring and checking the footprints library to make sure you have the right one. But, you know, just because I've used this before, I know it works, I'm just going to assign it to all the 1K ohm resistors. So we'll take a look at here, just make sure the values are correct. 3.6, 1.6, 7.62. Axial. Okay. And we can assign these to all the resistors. There we go. Great. So, now that that's done, you can see that the 7-second display and the AMS have been automatically assigned to their footprints. For the 7-second display, I'm going to have to go ahead and find out what kind of footprint this is afterwards, just so that students can download it, but for now, that's okay. And for the 74LS47, we're going to go to the DIP package, because DIP stands for dual inline package. So package underscore DIP. We're going to clear the filters here. And we're going to select package DIP, DIP-16 underscore W7.62. I believe it's this one. And we can check to make sure it looks right. Yep, it does look right, which means we are on the right track. Cool. Again, SPDT switches will have to come later on because I accidentally deleted my libraries, but that's okay. Capacitors. Now, the capacitors come in 10 microfarad and 0.1 microfarad types. For 10 microfarad capacitors, I like to use electrolytic capacitors, which are polarized. Usually for larger capacitors, you use electrolytic. For smaller capacitors, you use ceramic. So for electrolytic capacitors, I am going to use a very specific size of capacitor. Again, it's going to be a THT capacitor. So the size I'm going to use is, well, first of all, it's going to be radial. Okay, underscore. And then it's going to be D 4.0 millimeters. And we filtered it down to 2 of them. It's going to be the 7.0 millimeter height. So the 10 microfarad capacitors are going to be the same. Now for the 0.1 millimeter capacitors, or 0 millimeters, 0.1 microfarad capacitors, these ones are discs, right? So the DISC, disc underscore D 5.0 millimeters, and then we only have 2. And this is the W 2.5 millimeters, and then P, the pitch is 2.5. So this first one right here. Great. So now we have assigned the footprints to the capacitors. Now let's do the same thing for the LEDs. I don't know why my throat is getting drier than usual. Okay, for LEDs, we're going to use the LED underscore THT because, again, we're using through-hole LEDs. Again, I really like how KiCad's library is structured out. It's like really easy to access and everything. It's very nice. So LEDs, we're going to be using the 5.0 millimeter model, which is this one right here, LED underscore D 5.0 millimeter. You can check the footprint to make sure it's right, in which it is. And then our VN is going to be terminal block. So terminal block right here. And then we are going to have this as Bornier to pitch 5.08 millimeters, which there's only 3 of them, which is cool. So I'm going to go ahead and select this one. Just making sure it's the right one. Terminal block Bornier. Yeah, that looks correct. Okay. Now, the hard part about this is actually, I realized it hasn't actually assigned these diodes anything yet. Oh, actually, it automatically did. Oh, that's cool. That's cool. It automatically assigned it the part number, which it didn't do before. Okay. So now we're going to go ahead and create the footprints for all of these parts. And the footprints are going to be a little bit of work because I completely forgot how to make them. So I guess this is a learning experience. Let me just look at my chat real quick. I haven't been looking at it at all. I'm going to go ahead and black out this screen for a second. Oh. Thank you, Helen, for the Prime sub. Thank you, 20 Lush, for the follow. Thank you, DHR33TI, for the follow. And thank you, Bellum, for the gift sub to Twitch. Very much appreciated, Bellum. What are the chances the actual Twitch account will be able to come on the stream? So I'm going to find the data sheet for the switch real quick so we can make it slide switch 5 millimeters. It's weird how these like switches, I can only find the data sheets on Amazon of all things. Okay. So we're going to use this photo in order to figure out how to make this switch or make this footprint, which is interesting. Okay. So we're going to go to the KiCad main menu here, and I have a ton of tabs, which is hilarious. Cancel this. Cancel this. And then I'm going to go to this screen. Okay. Footprint editor. Now these 5 millimeter slide switches don't actually exist as a footprint. They're not actually supposed to be put onto like a PCB at all. So I usually make my own custom footprint for it, which is very fun. I have to remember how to do this because I don't exactly remember how, but I do know you have to create your own library. So let me go do that first. Pin library. Okay, how do I create a new library? Oh, here we go. New library. I'm going to make it global. I'm going to call it, put my documents, put it in KiCad 7.0, and I'm gonna make a new folder, call it 7.0. Or let me just put it as 0. Libraries. I'm gonna name this custom footprints underscore MSI. Learning by teaching. Oh, I'm teaching myself, so. Okay. So now we should have a new library on the side called custom. What? Custom foot. Where did it go? I did new library. New footprints. Through hole. Slide switch 5 millimeters. Okay, saving library. Where did my custom... Okay, my library just disappeared. Okay, let me try this again. New library, global. It's here. Custom footprints, MSI pretty. Do I have to add a new line? Or is it not looking in the right folder? Okay, I'm gonna have to Google this. Give me a second, guys. KiCad new library folder. Choose library for your folder. New symbol button. Add library. Wait, I think I have to add the library to the. Hold on. Okay, I have to add the library, right? I have to add this library. That's it. It's not it. I don't think it wants to add the library for some reason. Add library. Choose a library to add global. Wait, am I adding it to the wrong folder? It's supposed to be 6.0. It's supposed to be here. Footprints? Maybe? Oh, what am I doing? Okay. I'm not sure why new library isn't working for me right now. Prints. Library.pretty. Let's try this again. Custom footprints MSI. Where is it putting these things? Oh boy. Or maybe you have to add it to the project? Okay. Oh, that worked. Okay. I guess it's on project by project basis. I don't know. Okay, let's see. Can we save it? We now save it to custom footprints MSI. Great. Okay, so got through that initial struggle, but now we have to actually make the dang footprints. So I'm going to use this diagram here to do this. It says the pins are 4.7 millimeters apart, which is fun. On the side, it's 1.3 millimeters thick. Okay. So, start with the pad. Actually, we start by moving this stuff away first. Get out of here. You start with a pad. Maybe like, I don't know what the dimension of this is. This is 2.5 millimeters. The grid facing is. Oh, wait. Grid is I'm gonna put it as 500 mil. Use ChatGPT to make the footprint. Actually might be a viable solution. Okay. Problem is, hold on. So, mil is thousandths of an inch, right? So this would be 50 mil. I need 500 mil. Is this 4.7 millimeters? It looks like 4.7 millimeters. 5.08. Okay. So, okay. I think I have it right. I'm going to change this pad number 1, and I'm going to make it the diameter of the pad, or the hole shape. Diameter of the hole shape is going to be, let's see here. I'm going to do a millimeter to inches conversion. And my whole screen disappeared. I just heard mill and I thought of manual aluminum mill because I worked on it for too long today. Not that kind of mill. Not a CNC mill. A thousandth of an inch mill. Okay, where's my picture? So this thing is 1.3 inches, or 1.3 millimeters. So 50 mil, about 50 mil, 0.5 mil. So if I want this thing to stick, I'm going to give it a small tolerance, 1.5 mil. So this will be 0.06, I think. And so I'll make this 0.08 for it. I don't remember like how I made the previous footprint. Actually, I can find it, right? Let me find it. Okay, this is a good thing about having like stuff that used to work, because I can go find out where it went. For Blinky Learner 2, I definitely used a SPSD switch. You should strive for bills instead of mills. I have a video for you when you're done doing your pilot lesson today. Oh, thank you, Escabite. The stream's still running okay? Nothing's dying on the streams? I know custom components is not found. Chill. Yelling at me because it doesn't know where my custom components are because I deleted my libraries. Okay. Luckily, I still have my switch, so I know how to recreate it. Okay. So, this is what we need to create. This is what we need to recreate here. Okay. Don't mind the infinite KiCad tabs. So these pads, they're 0.075, okay, and then 0.125 pad size X. 0.25, 0.075. And we have them of 1, 2, and 3, I think. 2, 3. Okay. And then we put a line around it on the front silk screen. It's kind of like, I'm just gonna directly copy it from the other footprints. Don't mind me just doing a little bit of stealing. I have to put the grid size down. There we go. All right. Looks like it's centered and everything, so, and then I just have to change the reference and call it switch mode, or hold on, sorry. This isn't a specific footprint, so I'll just leave it here. And put this even lower. There we go. Boom. Boom, done. Save this, and we've got ourselves a nice little footprint. You have to cite yourselves as a source, otherwise it's plagiarism. All right, I'll cite my source. I'll cite myself as the creator of the custom footprint for Slide Switch 5mm. Well, I'm gonna head to sleep, but don't burn anything down. Thanks, Bellum. I will see you later, hopefully. Okay, so now that we've got our custom footprints for Slide Switch 5mm, we can go back to our other our other file right here, and assign our custom footprints to the switches. So we're back on track, like the Geometry Dash song. Ah, yes, custom footprints. There we go. All right. Now that we assign all the custom footprints to the right locations, drinking some water, we're going to go ahead and implement them onto the PCB. So just doing a quick electrical rules checker really quick, just to make sure I didn't do any big issues. Says I have a lot of issues here, but just don't worry about it. Yeah, I don't care. Okay. Let's do update the PCB from schematic. And let's get some, we're now going to move into the PCB side of things. Oh, hold on. Uh-oh. Oh, that's not good. Did I save this? Guys, I think it crashed. Oh, no. Oh, no. That's not good. That's very not good. Guys, my KiCad crashed. Okay. Yeah, no. Oh, no, it doesn't like that. Canarsa, you're a little too late. You're a little too late there. Oh, please have an autosave. Please have a backup. This KiCad's not responding to anything now. I think it might have crashed. Hey, at least I recorded this. Okay, no, it crashed itself. Oh, please have a backup. Well, this is potentially embarrassing. It appears the last time you were editing one or more schematic files were not saved properly. Yes, restore my save. Oh. Oh, good. Oh, good. It did save. Oh, thank goodness for autosave. Oh, thank goodness for autosave. That would have been potentially terrible. Okay, let's try this again with the schematic open. Oh, that would have been bad. Let's see if my footprints have been assigned. Oh, please. Please, computer. Okay. It doesn't know where my footprint pretty is, but, you know, it's fine. Lesson in saving. I'm very glad that KiCad automatically saves for me, you know? There we go. Okay. Now on to our favorite part of this whole experience. Wiring this all together. Okay. So this is my favorite part of all of PCB design. So now that we are in this location, what we are going to do next is to place every component into a location that seems like adequate for, for what the eventual thing is going to look like, or what the eventual. This is new. Oh. The net numbers are now 010203. They're no longer like actual nets. That's very new. Anyways, what we're going to do now is we're going to place each component on the PCB as if, we are making the PCB itself. These are footprints, so they're going to go on the eventual PCB. If I press the command Alt-3, you'll see a 3D model or a 3D version of the PCB here. And you'll see that an error message says the board outline doesn't exist, but we'll clarify that in a bit. So, explaining all the concepts going on here. We are going to go ahead and use the schematic. This button just transfers between the schematic and the PCB. We're going to use the schematic in order to place every component into, a visually appealing location. That's what eventually going to be made for us when we, make this out to order. So we can see here that our user inputs, usually for user interfaces, you want the user input to be like on the bottom or on the side or like somewhere on the border so that it's really clear to the user as to what it is. So in this case, switch 1 to 4 are going to be user input switches. So I'm going to go ahead and drag these outwards like this. And switch 5 is the switch to turn everything on. So I'm going to move everything outwards for now. I'm going to put switch 1, 2, 3, 4 in line with each other, kind of like this. And what I like to do usually, what I like to usually do, is I like to make sure that everything is in line. Maybe I can put like the switch up here. So these are going to be the user switches. Actually, I'm going to rotate them 90 degrees so that, you know, off is down, on is up. Do this, switcheroo, switcheroo. And I'm going to grab these, rotate it 90 degrees, put it up here. This. Just so that's more visually appealing. You know, this is the part that takes the longest time, which I'm going to spend the longest time on this stream doing, really, because I want to make sure that this is like the role model PCB that can be used for showcasing what it looks like. Tomorrow I'm going to, or during the workshop, I'm going to speed run through it, but you know. I think it bothers him deeply when I send him highly asymmetric PCBs. You are correct, Ad Sandwich. It highly bothers me. Like, I spend a long time. You don't know how long I spend just making sure that everything is, like, symmetrical and organized. And also the fact that you don't, like, modify your, like, part names and you just leave them as, like, U1, C1, Q1. That highly bothers me as well. Yeah, it's a stupid amount of time, but it's all worth it at the very end. It's all worth it. Hopefully. Okay, we have our user input switches right here. What I'm going to do is I'm going to put the on-off switch on the side, a little bit spaced out, and then I'm going to put the regulator circuit like right next to it. Generally for circuit design, oh, that's a new feature. Half of like this stream is just me figuring out new things that KiCad 7.0 has put out. But we want to put the power supplies or the power switches very close to each other, especially the capacitors. You don't want to put capacitors like really far, because if you put it really far, then the filtering effect's not going to work. You have to know that when you're wiring things on a PCB, it's good to keep everything as compact as possible, just so that the signals can travel from component to component, like directly. Because it's way better, if you think about this in the real world, if there was like, let's say a capacitor was a supermarket and the AMS was your home. If the supermarket was right outside your home, then you would be much happier than if the supermarket was like 16 miles away, right? So again, for power things, because you can think of like power transmission as like driving. You don't want to drive 16 miles to the supermarket. You just want to like go outside and boom, there it is, right? So the power circuit is going to reside really, really close to the switch, the power switch, and also the terminal block. So usually I like to put these two circuits together, right? And I usually like to put the diode right above the power switch. Actually, yeah, above it like this. Just so that's easier to work with later on. And then I'll put the AMS right here. Unless the supermarket costs too much for you, then all the people there annoy you and you refuse to send radio signals. That's a more complex topic, but that's really funny. Radio signals are finicky. As I've worked with them with Ad Sandwich, and he has yelled at me for my mishandling of radio signals over the past few times I've done PCBs with them. Still getting the hang of those, but like regular signals or like regular components like this, I can do completely fine. So you put me in radio, like the terms of like radio signals, that's where it gets tricky. Okay. Okay, so I'm gonna put the capacitors right here. Actually, I'm gonna put the capacitors like right here. This is a nice location for them. Like the more you do PCB design, the more you get an eye for these things, and you start to be able to like see evenness between the two components. That's kind of like my favorite part. Is just trying to get everything as even as possible. It's so fun. I'm saying this as ironically as I can, because I sometimes spend like way too long doing this. You'll be sitting at your desk staring at a PCB for like hours on end, wondering like where your life has gone to. You're trying to you're just trying to figure out why the heck your things aren't centering correctly. Okay, now I know that this kind of 7-second display is kind of flawed in a way where it's not wired correctly, so I have to like look at the other Blinky Learner sticks. If you want to do more reference to Shift P, what is Shift P? Oh, position relative to reference item. Oh, that's fun. You lose time so easily working on PCB. That is so true. That is so true. Okay, so LEDs 5 to 8 are going to be the LEDs for that one. So LEDs. Wait, no, that was the resistors. 5 through 8 is boop, and then LEDs is D1 to D4. So right now we are just positioning. And for these LEDs, okay, well, these resistors came directly to here. Again, you kind of want to make sure that everything is like as compact as possible because, you know, space is also money. Like the larger you make your board, the more money it'll cost to make it, to produce it. It's a really weird kind of like relationship, love-hate relationship with LEDs, or with PCB design, as I like to call it. I'm gonna have to fix all the like spacings with the letterings later. So these represent the. Actually, I'll have to switch all of these because I want the LSB to be on the right. Yeah. So I'm gonna put a marker. I'll put a marker over here. It's kind of like where this location is, and I'm gonna like switch these two. And I'm gonna switch these two. Like it's also really hard to hold like a comprehensive PCB design workshop because I feel like even with my experience in PCB design, like I haven't even scratched the tip of the iceberg. It's like such a wide skill set to have, and both as Sound and I do it for a hobby on a hobbyist level, which is why we don't make complicated PCBs, but we do it for fun mostly, which is why KiCad's so great. Okay. And then I just got to do this, or make this in sync with it. This is 04. So it's over here. So something like that, kind of. Or maybe. I don't know if there's enough space for that. I'll put like underneath. I don't know if there's enough space for that actually. Yeah, no, it overlaps with each other. Not cool, man. Okay, how do I make this like visually appealing? Maybe shift everything to the right. Or, okay, I think I got it. I'm gonna shift this to the left, this to the right, this to the left, this to the right. Or no. I should have no. Okay, now everything is left aligned, and then the resistor goes to the right. I've solved it. Like that. Okay, 7, and I can adjust the spacings of it later. I can't hear audio, but I don't know if you guys can hear the raid notification. But thank you, Roughsu, for the raid, and thank you. I will enjoy my stream. I hope you have a great rest of your night too, and a well rested sleep. I can't hear anything right now because my headphones automatically turn off after a while of inactivity, and it's been like a long while since I last was active on them. I don't even know why I'm wearing these. Maybe just to like hide the sound of my voice. I don't even need these anymore. Okay. All right, so now we've gotten this to work. Actually, I'm going to put this LED right here just to indicate that's been on. The LED that indicates it's been on is D6. Oh, and the resistor is R9. Resistor. 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 All right. Okay. So, I'm going to put this net here. I'm going to put this net here. And then that looks fine. Okay. So now we've got everything laid out really nicely in this kind of like array pattern. Here. Okay, we can get the rest of the resistors to go on now. I believe the rest of them. Why do I have so many resistors left? What are these for? These are for... Oh, these are the pull-down resistors for the switches. Oh, I see. Oh. Oh, that's an issue. Okay. So, these are pull-down resistors, which means they should... Oh, man. Okay. That's difficult. Well, it's not that difficult. You know what? I'll just put them. I'll just put them right here. So 04 is going to be right here. No, that won't work. Will it work? Oh yeah, you run into a lot of deliberations when you're doing this kind of stuff. Like, should I put the resistors there? Should I not? Like, what to do? What to do not? What to not do? I think like what the best option I have actually is if I space these out a little more to the left and put it. Okay. Yeah, I'm going to put all of these resistors over here on the right in this pattern. Yeah, that way will be easier to put down later. So 1, 2, these don't have to be like as close as the other ones, I don't think. Just like this would work too. 3, 4. Position them nicely later. These pull-down resistors will make sure that it's getting the correct signal. It's getting the right message, you know. Okay. This is bugging me, the fact that the bottom is not aligned. Okay. So like the last thing is this chip. It's a fat chip. Going back to the 2.5. So I think what I'm going to do is I'm going to put this chip right here in the middle. That's the middle of it, actually. Okay, this one can go right here. There's one more resistor, right? Wait, where's the resistor for? Wait, I thought there was a resistor for this one. Oh, there wasn't. Uh-oh. Ha ha. I forgot one resistor. So there has to be a resistor from the 7-segment display to 5 volts because you need to make sure that the LEDs don't blow up. So I'm just making this 330 ohm. You know what? It feels like weirdly quiet if I don't have my headphones on. So I'm going to put it back on even though there's nothing playing through it. Going to give this a footprint and then F8 to update. Okay, there we go. There's my resistor. Ghost noise. Yeah, it's basically ghost noise. Okay, I'll put this one like right here. Just to indicate that's next to the 7-second display. Okay. Maybe I can stuff this. No, this looks fine. I'll have my title here. Logos and stuff. Yeah, I'll be fine. So, you have a bunch of nets. All right, let's see where this goes. So now that I've placed everything onto the PCB, the next step is routing. Routing is fun. Actually, routing's not the next step. The next step is actually to place all of the... next step is to place all of the board outlines. So on the right-hand side, you can click on this thing called edge cuts right now. And what edge cuts does is when you put down lines, they'll actually be, they'll actually act as the edges of your board. So if I have like an edge cut right here, and I like having like rounded edges to my board, so I'll talk about that later. I usually have like mounting holes for these boards on all 4 corners. They make it look more modern and neat. You can just do them like at like a wide angle. You correct them later. It's not much of a big deal. Something like that. Okay. Now this is the cool thing that I've kind of developed over the past few times I've done this. Is I have a specific way of making my board shapes. I like them rounded on the edges because I once stabbed myself with a PCB and it drew blood. So now I am scared of sharp PCBs and I will never go near them again. So what I do is I like to take like a line from one of these corners, and I believe so I need to go 0.2 from the top and 0.2 from the side until you get to 0.2828. So I will do this for all 4 corners, even though it might stem into the middle of the board. So 0.2 here, 0.2 here, 2828. There you go. Vengeance upon that silicon. I guess you could say that. Okay. And then what I'll do is I will go ahead and make semicircles. And the semicircles always go clockwise. This one will have to move to the right. Maybe like even more downwards. Something like that. Sure. And I make arcs that go on these directions because arcs are cool, and if I have arcs, I won't stab myself with them anymore because they'll be bendy, or filleted. It's like or fillet or fillet, whatever you want to call it. Fillet inside of a CAD program. Right, so I make sure that all of the corners are bendy. Now it's weird because actually I'm going to go ahead and move this part up. I usually have mounting holes on all 4 sides of the board, but I'm making an exception this time because I just want to maintain how symmetrical it is on all 4 corners. So I'm going to take this bottom half, and I'm going to move it up until it's like really close to the switches right here. And I'm going to remove that and just put it inwards. Yeah. So it's going to be... No. I messed it up. So it's from here, 2.2828. And then... Okay, it's like slightly off. So I was like worried about. Usually it's not this much of a pain in the butt, but it looks like it's slightly off, which is not good. But you can like correct for it a little bit. Okay. I don't know why that looks a little bit off. I just don't like that for some reason. The top ones are fine. The top ones I can stand. Oh. Maybe it's like with moving this to the right, it's just not locking on anymore. Maybe that's why. Like this. And then with this moving upwards. Okay. That corner looks fine. This corner does not look fine. The top left corner. Again, this is like why you can spend so long doing PCB designs. It's just because you want to make everything look perfect, because anything you do here is going to be made into like a PCB or made into a physical object later on, and you want to make sure that physical object doesn't get ruined by your imperfections. Okay. Just test it in production. You know, me 6 months ago would have agreed with you on that point at Sandwich, but me now, knowing what I know about testing things in production, I'd rather spend a few extra minutes looking at it inside the design rather than producing it. So I think that looks fine. I don't know. Oh, that still looks wrong for some reason. Oh, maybe it's because... Oh, I know what it is. Maybe it's because it's just not symmetrical on either side. Right? Yeah, there's like so much more of a gap on the right side than on the left side. Let's try this. Okay, I'm gonna adjust that so it's like, oh, that's very close. That's very close. That's very close. Okay, do 4-way. Do 3. 2, 3. That meets. That meets. That does not meet. Okay. By complete accident, I have never developed a PCB that doesn't work or has incorrect labels because I don't label. However, I tend to have spacing problems, which are generally overcome in non-standard ways. Yes, your ways are quite the standard to uphold. I'll say that. Okay, now I have to figure out how to put like a mounting hole on the corners. I can probably move everything like on the left. I can move the V in upwards. That I can do. Okay. What I'm gonna do is I'm gonna have this move upwards, this move to the right. Don't remember if this was the front or the back, but I'll check in a second. And so what I'll do is mounting holes. I usually have 0.2 millimeter mounting holes. That fits the M2.5 screw. I should have removed these lines, by the way. These lines are how I gauge where the center is for those holes. This is just like my own technique because I like mounting holes because I like printing cases for these things eventually, and it's just a great way to, you know, finalize your work after you finish it. Okay, so then again 0.2. Oh, well, it's is it 0.1? It's 0.5, right? 100 mil holes. I think it's 0.5. 0.5, 0.5, 0.5, 0.5. Okay. So then I gotta move everything here to the right, but that's okay because so this goes to the right, this can go to the right. And I'm gonna move everything here to the right. That creates an issue because now everything looks off-centered on the left side, but this terminal block, this VN is going to go up here, probably, which is not a bad place for a VN, honestly. But this LED is going to have to go places. So this diode can still go, well, this diode will have to go vertically. So it'll go vertically here. That'll be net. Okay, this diode will fit in this location. And now to find a place for this LED, which can go over here. Oh, perfect. Oh, let me tell you that this switches this. Whew. So in general, this is a good hole size for a M2.5 screw. But if you want to know if it'll fit, here's a neat trick. So 50 mil is the inner diameter of the screw, but on the head it's about 100 millimeters. So 100 right here. So if that doesn't touch the LED, we're in good hands here. So it's barely gonna fit, like barely. But hey, who doesn't like living on the edge of it? Okay, that should be much more bearable. Alright, now that we've squished the LED, we've squished the VN port, we've squished the diode, we've squished the 7-second display. We squished that. This can like go places. If that's the center, then that's also the center point. Okay. You can save the VOD of this stream and just replay for Friday. I'm gonna spend like an eccentrically long amount of time positioning. I'm only doing this for stream. Like during the workshop on Friday, I'm literally just going to like place things in random locations and go like good luck. But I want to at least have a good model here before I go off and go crazy tomorrow. You know. Oop, whoa, 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 whoa. Control M. Wait, is the Control M no longer measure? Oh, it's Control Shift M. Okay. That looks like the center between the 2 points. It's good enough. Okay. So what I'm talking about here is now that I've placed everything, you can see that the edge cuts automatically register with the 3D model. So if I do a control 3, you can see that now. It looks pretty decent. It doesn't look too bad. So it's a rounded board, which is good because I'm going to cut myself or something if I don't have it rounded. With mounting holes on every 4 corners. You'll see the silk screen. The silk screen is the silk screen is the top layer of the board where labels are usually written. The white things are all silk screen, and all the screws should fit. Let me just test this one on the bottom here. Yeah, it's gonna fit. Okay. So now I'm going to go ahead and just hide all the silk screen and the courtyard. Oh, not this one. Back courtyard. No. User drawing. Is it user drawings? No. Okay. It's FFab, but sure. I think everyone on stream is dying to see me route this thing. Okay. So during the routing process, you have to ask yourself the question, how much current is going to go through my board at any time? And in my case, I don't think I'm going to exceed a current of 1 amp. So IPC standards for 1 amp is about 15 mil, which is what I'll use for the entire thing. But if you have like varying currents, such as if you're using this to power a solenoid or an actuator or something that draws like 2 to 3 amps, you're going to have to use like 30 mil, 50 mil, anything that's a higher and can handle like a higher amperage. Or you can just do what Ad Sandwich does and put like a whole polygon pour across the 2 areas, but it's up to you. I like to use 15 mil, 0.015 inches, and I'm gonna keep the grid at 2.5 just because it's a nice connection. And then I'm gonna make it grid 0.01 just so I can connect properly, and then I just start connecting. It's not shots fired. It's actually a smart idea. Massive polygons. It was pretty funny though. I'm not gonna lie. Like whenever I ask, oh right, I forgot about polygons. Okay, actually before we start routing, I need to talk about polygons. Polygon pores is going to be called a filled zone. Oh, thank you for the drink, Bork. I needed that. All right, we're 2 hours in. I'm predicting that this is going to be a 3-hour stream. Okay, polygons are large areas of copper that have connectivity between multiple points. So, you know, for polygon pores, they're called field zones in KiCad, and we can put them on our board on the front and on the back. I'm feeling parched from all the talking. I'm going to put it on the front copper. So before you put the polygon pore, make sure you're on the right layer, first of all. You can choose the layer on the right here. And then you're going to put them on the front and on the back. And you can choose what connects to these polygon pores. And hi, IE76. Nice to see you. Oh, and thanks for the follow. I don't have follow notifications on, but thank you. Okay. And you're going to put this copper area around the entire board. Now you can choose what to go on the front and what to go on the back. Usually what I like to do is I like to do like 5 volts on the front, ground on the back. Makes a really big capacitor basically, and covers a lot of the pins, because when you're routing you have to connect all of these like rat nests lines, and it might be a little bit difficult to do so if you connect all of them and don't have some removed. So in this case I have put 5 volts on the front, and if you press B to re-pour, you can see that everywhere that needs 5 volts has kind of like a connection to this polygon pore plane, right? So I'm going to do the back now. I'm going to go to the back copper layer and then just use the front. I'm going to make it ground because I have a lot of ground and I have a lot of 5 volts. This just covers a lot of area for me so that I don't have to route it later. The KiCad shortcut for pouring is B, just the B key. And you'll see that now I have a lot less things to connect in general, right? And priority in case you have these things all over the board and override each other. Yes. I mean, I don't have to deal with like multiple connections yet, but you know. Okay. So, Control B removes all the pores, and you'll use B and Control B a lot in KiCad, because a lot of times when you're routing, you don't want to have that polygon port be in the way of your work. Because, like, look, it's just like a lot of mess, and if I try to connect stuff on the front plane, it's just going to look like a mess because it's brown and red. But if I do Control B and just start connecting, now it looks a lot more bearable to look at, in general. Okay, let's do some connecting. So connecting is pretty simple. You just follow these lines and try to get a good connection between these 2 points. So when you click on a terminal, when you click, when you click on the terminal and you press the X button, and I believe the X button is the one that allows you to move things. Hold on. Okay. So X is wire, and so you'll connect each terminal. When you press X on a terminal, it'll show you what it has to connect to, right? Again, if it's a 5 volt or if it's a ground, just completely ignore it for now because, again, remember, you have the polygon port. It's going to cover it all. It's going to be really nice. So in this case, the diode has to go to these 2 points. One is the LED, right here. The other one is into the AMS. So we'll just do that real quick. And the last one is to the capacitor right here. Now, general rule of thumb, you kind of want to avoid, it's kind of like a puzzle game at this point because you're trying to connect everything together and try to minimize the use of vias, so like vias, or however you want to call it. Vias are areas of the PCB in which it passes all the way through the board. So it connects both sides of the board together. And it allows you to pass through a trace, essentially. It's kind of like phasing through it. You'll see if I have this trace going from the net D5K and going across, you'll see that I can't actually connect this 5 volts, right? So that will be a little bit of an issue. But then you remember that, I have a 5 volt polygon port, so I can just probably, press B and then it'll connect itself. So that's in general is fine, but just making sure that you have all your bases covered. So let's go ahead and keep going. It's a fun little puzzle game. Another rule is you generally want to avoid. You can avoid right angles because you don't want to have maybe this. It won't look too nice as a right angle trace. Now it's not really much of an issue if you don't have high frequency signals, because then high frequency signals, it won't be able to pass that turn. But if you have low frequency signals, like a DC voltage, there's not really many things switching in this circuit, so we don't have to deal with that kind of signal, that kind of problem as of right now. So I'll bring the attention to this 9 volt here. If I try to connect this 9 volt on the red plane, I can't pass through this section, right? It tries to auto direct me around this and into this VN port, which is kind of not ideal. So what I want to do instead is I want to go to the back copper plane, and I can go into the back layer, because remember these are 2-layer boards. So I can go ahead and just route this like this, and you'll bypass this restriction because the red line is going to be on the front, green line is going to be on the back. They can cross underneath each other. That's the beauty of a 2-layer board, right? Another general rule is try not to get these lines too close to each other, because if you do, then weird stuff will happen. Okay, just pressing B again to check what I've done. You can see that on the front and back, the polygon port automatically adjusts so that it goes around what you've worked on so far. So you see on the bottom right corner, everything over here has already been covered. So I can do Control B again, and I can see that I can just work from right to left, covering all my bases. Generally, I like to work from the power side of things and then cover the rest of the circuit afterwards. So you can see now I have covered most of the power logic and the power side of things. Now I'm going to move on to the switch, the user input section, because the user input section is the second easiest. Control B. And on the front copper plane, I'm going to go ahead and connect these all together. These are really easy because it's just a direct connection, right? Like that. And then for these resistors, I'm just going to connect it downwards like this. Oh. Actually, probably upwards. Again, these are some of the easiest connections because they don't have much going on with them. It's just a straight line. And then I might even go ahead and do these connections right here. where it's the pull down resistors. And I can go ahead and do this. I don't like that. Oh, I can do it from here, actually. That's a better idea. Okay, and then O3 is over here. Pass it through the switches, and O4. Pass it to the bottom switches. Now, normally you don't want to do this kind of thing where you pass it in between two pads, especially if it's like a small pad like an Arduino. But since these are switches and these are like absolutely giant, there's no issue at all with me doing this. It's not going to do any harmful effects. Probably the one thing it's going to have an issue is these 5 volts are not going to get covered, but it looks like these are, so that'll be fine. It'll be fine. It'll be okay. Okay, now we can see that most of the bottom areas are covered. Now it wants me to start connecting things over to the 74LS47. So let's go ahead and do that. Control B here. So it wants me to connect things like the net UIE. These are going to go basically from... Oh, these ones are going to go to the 7-segment display. And actually, it seems like a lot of the ones on the bottom are going into the pins. So it would be much better for me if I just flip this around from the center. Actually, if I did this correctly better. There we go. So such that I can connect the O1, O2, O3, O4 directly from the circuit on the bottom, and then everything else on the top goes to the 7-segment display. That way it's a little bit better for this overall, and minimizes the amount of connections I have to make. You'll notice that the O1s, this is kind of trapped in between everything else. So for me to get O1 over there, it's best if I use the back copper plane. So I can go ahead and go straight from here, and go around and up and into the pin, right? Same for O2. I guess O2 I don't have to do that because I can just go, actually I can go through there. It's a little bit sketchy, but I can just use the red plane. The reasoning behind this is because if I use the green plane, then O3 and O4 are going to have a hard time getting around too. So just thinking ahead. Okay, just snaking around, trying to keep in the center lane, just so that it doesn't disturb any of the other signals. And now for O3, O4, I kind of have to use the green polygon pores, which is the issue for O4 because it can't pass through, but it won't be too much of an issue. I can just go downwards and up and around, like that. There we go. And it looks like a bunch of spaghetti. Which it is, but everything's connected and hopefully it doesn't pose too much an issue for these connections here. And looks like it's fine. There's like less and less lines now. Oh, there's one issue in which we want to connect this to ground, but that's okay. Because these are SMD pads, so it doesn't go all the way through to the other side. So now all I have to do is connect the lines from the 74LS47 to the 7-segment displays, and then that'll be the last type of connection I have to make. I'm just going to quickly connect these up first. Like that. Oh. And then down here. Okay. Okay. Now this is the complicated part because I have to make sure that it connects this correctly, because I know that when I downloaded this 7-segment display, it didn't quite accurately represent what was actually on the 7-segment display. So this goes here, and then D goes here, E. Okay, so you see how E, I have to like kind of go under and do weird things to get there. So I'm going to use a green line for this, so it just can go straight through, and this is going to go on the top. Here is going to go there, so I'm going to use a red copper line for this, and they can go on top of each other because they're on different planes. That doesn't affect anything really. and then this one. This one is going to go over there. Now here's an issue. This is a fun issue because we have the green line there blocking it, and there's no way for it to get past this unless you do something weird like that. So in this situation, we might have to reroute maybe this wire, maybe C, and use the green line to go through underneath. You don't want to slab it with a via just yet, you know. And then it looks like this one can just go underneath here too. As we said, like, there's a lot of connections you got to make with the decoder. And so if you can put them on a PCB and not have to like connect them with wires, that'd be like the best option you can have. So I'm going to delete this wire because it's blocking the way. And then connect this with a line here. And then with this section, I can just use the green green area to connect this last point. And then I don't have to use vias at all. Right? If I press B and repour, it looks like everything has been covered. I can look closer at the board to make sure that there's no like weird looking pores or lines or whatnot. Okay, I do see something weird though. Generally, you want to avoid something that looks like this, just like weird little random pores that are in between lines that don't really like work out. So for the way to fix this is just to make a keep out zone. Just make sure you keep out tracks, keep out vias, keep out pads, and you just draw it around it. Just to make sure that, I'll do it again. This doesn't happen. I'll remove this too. Like that. And then even like this small area here. This is bad because it's like an unwanted space. Because like these kind of traces, they act as a pseudo antenna. So if I do B and repour, zone, rural area. Did I do the keep out area wrong? Keep out copper fill. Oh, there we go. Keep out copper fill. Keep out copper fill. Okay, there you go. So we don't want any antennas in our design. At this stage, usually I spend a long time just staring at this board, seeing what could be improved, and whatnot. But I think as of right now, if we go ahead and do Control 3, we can see that everything has been connected using these 15mm lines. Oh, I see one right here. You see that little piece right there? That should not be there. So this one is just going to be an extension of this keep out zone. Repour. There we go. Now that's gone. And we can look at the model again. If we want to see things like 3D models, we can toggle them on. Like that. The switch doesn't have a 3D model because I didn't make one for it. Neither does the terminal block, but the IC chip does. The resistors and the LEDs do. Looks pretty nice. So the last step to make this PCB look better is just to relabel all of the silk screens to the right values and just make it user-friendly for the user. Add maybe like text on the screen, attributions, whatnot. I'm not going to do that on stream because that's really boring, but I'm going to tackle this when I'm offline and get a model PCB up and running to showcase for it. But in general, this is what it should look like. This is the whole design process from start to finish. I did it in 2 hours, but I know that's not going to happen during the workshop on Friday. But this has been due to like all the in-person logistics and whatnot. But this has been a cool little demo of what to expect so far. And you know, I'm gonna order this PCB too and test it out and whatnot. Everyone should share their follow-along schematics in the project Discord. I don't know if they've been following along, Condarsa, To be honest here, like, love the optimism, but I don't think they've been following along. Okay, I mean, if you have been following along, put in the project Discord. I will look at it. But thank you so much for watching today's stream. I know it's been a long time since I last streamed. I'm getting a little rusty. I'm tired from 2 hours of talking, even though I do it like every Friday nowadays. I have one. Congrats, Kandarsa. If you want a free PCB, let me know so I can order it. We have this program at our school that if students follow along or they make their own PCB, I'll make you print the case. All right, fair enough. If students follow along and make their PCB, they get to like order their own personalized one afterwards. I think it's pretty cool, and like we teach them how to do Gerber files and activations as well. Okay, I'm gonna leave it here. Thank you so much for watching today. Hope you enjoyed. If you did follow along, put it in the Discord. I'll take a look at it. But yeah, it's 12. It's midnight. Oh my goodness. But yeah, thank you so much for watching. Have a great rest of your night. Have a great night's sleep, and I hopefully see you sometime soon. I can't say tomorrow anymore because I can't say tomorrow anymore, but sometime soon is good enough for me. Let's go ahead and raid someone if someone's even online. I don't even know if anyone's online anymore. It's been so long since I've been on Twitch. But yeah, let me turn on my headphones again. Oh, Kenshi's online. Cool. All right, we're going to Kenshi. Oh, yes, save my work. Thank you. I'll save my work. All right, let's hit Kenshi up. See ya.